Voyager 1 is a space probe which launched in 1977 as part of NASA's Voyager program for studying the outer solar system, a cold, vast and mysterious expanse far away from the warmth of the Sun. Voyager 1 completed flybys of the gas giant planets and their moons within 3 years, and by the 1980s, the probe was on a trajectory out of the solar system and into interstellar space, the final, extended part of its mission. In the nearly 40 years it has been travelling since, mankind has managed to study all 8 of the solar system's planets, as well as the handful of circumstellar belts that lie in between. However, the solar system is enormous, extending over billions of kilometres, and the space between these star systems is even larger. Voyager 1 travels at around 17 kilometres per second, covering just under 1.5 million kilometres a day, yet it will not approach by another star in the galaxy for some 40,000 years, long after it becomes defunct and radio silent. During this long, lonely voyage into the wilds of the galaxy, the probe will pass beyond the icy reaches of the outer solar system, lying deep in the boundaries of interstellar space. It will eventually become the first man-made probe in history to reach the very outer edge. But what lies at the outer edge of the solar system? It's not a planet, and it's not a belt like we see in the inner solar system. It is, in fact, a huge diffuse cloud of trillions of icy objects, a kind of shell for the solar system, probably extending into space for over a light year. It is the Oort Cloud. The Oort Cloud is a hypothetical bubble of icy space debris which extends around the entire solar system, ranging in sizes from particles right up to mountain-sized fragments. The vast majority of these fragments consist of water and methane, among a number of other elements and compounds. Unlike the orbits of the planets and belts in the inner solar system, which are all aligned with the rotating orbital plane of the Sun, the Oort Cloud is a giant, all-encompassing shell of material which surrounds the solar system at a distance thought to be several thousand times further than the orbit of the Earth. It is thought to expand out into interstellar space for trillions of kilometres, and is the most distant area of our solar system, defining the boundary of the Sun's Hale sphere, the farthest point at which it is able to attract satellites with its gravity. Out here, the Sun is nothing more than a particularly luminous star amongst the many billions of others in the Milky Way. Because its contents are only weakly attracted to the Sun, objects in the Oort Cloud do not orbit along its plane or travel in the same direction. Instead, fragments shift, move and tussle each other. Their loose attraction makes them particularly sensitive to gravitational disturbances from nearby stars and also from the galaxy itself, which can send objects within the Oort Cloud on trajectories towards the Earth and the Sun as comets. Due to its sheer distance, darkness and sparsity, no object has ever been conclusively identified within the Oort Cloud, but it remains the most widely accepted explanation for the source of the distant comets that we see entering the solar system. Objects in the Oort Cloud, and all those beyond the orbit of Neptune, are known as trans-Neptunian objects, and the distances of these objects from the Sun increases by orders of magnitude the further out you go. When we cross beyond the orbit of Neptune, the distance from the Sun is so immense that we have to think in terms of astronomical units rather than kilometres. An astronomical unit is the distance at which Earth orbits the Sun, about 150 million kilometres. At 5 astronomical units, so 5 times further than the Earth, is the snow line, the boundary beyond which it is cold enough for water and other substances to exist as ices in a solid form, resulting in lots of extra material further out from the Sun. Neptune orbits at about 30 astronomical units. Beyond the orbit of Neptune is the Kuiper Belt, a thick, spinning, donut-shaped disk of billions of pieces of ice and rock left over from the solar system's formation. The Kuiper Belt extends from Neptune to around 50 astronomical units away. Contained within are about 100 million comets, as well as minor planets and planetoids, like Pluto, Kuiper, Makemake, and even Neptune's moon of Triton, which is thought to have formed within the Kuiper Belt before being captured by Neptune's gravity. The Kuiper Belt is one of the furthest and most remote places in the solar system, but even these immense distances do not compare to the scale of the Oort Cloud. Light, travelling from the surface of the Sun at just under 300,000 kilometers per second, takes about 4.5 hours to reach Neptune's orbit, before taking another 3 hours to cross out the other end of the Kuiper Belt. It then travels for another 10 hours or so before reaching the heliopause, where the solar wind and plasma radiating away from the Sun collides with the radiation and gas of the interstellar medium between stars, like a galactic estuary, marking the end of the Sun's magnetic field influence and the boundary of interstellar space. But even this space is only within 17 hours of light travel time, at about 123 astronomical units from the Sun. The Oort Cloud's inner edge is much further, at least 10 light days from the Sun, maybe even further, completely dwarfing the scale of the planets and the Kuiper Belt. The cloud's inner edge is thought to begin at about 2,000 astronomical units, 40 times further away than the outer edge of the Kuiper Belt, and that is just the innermost point. The full structure is thought to extend as far out as 100,000 astronomical units, over a light year into interstellar space. And so, while it takes nearly a fortnight for light to reach the inside, it takes 18 months to cross out the other end, even at the fastest speed in the universe. Much of the material left over in the early solar system settled into belts in the inner solar system, like the Kuiper Belt. So the question is, how did all of the material in the Oort Cloud get so far away? Well, much like the Kuiper Belt, the Oort Cloud is believed to have formed, in part at least, from the remains of the protoplanetary disk which formed the solar system and the Sun's orbital plane. Matter condensed into dust and rocks, which eventually formed large pieces of protoplanetary chunks, called planetesimals. There are multitudes of these in the early solar system, and most were either swept up into the gas giants or ejected as the gravity of Jupiter in particular scattered them beyond the snow line and on a trajectory to their distant, remote position. Trillions of pieces of debris settled into the belts we see in the inner solar system today, but the rest was flung out beyond the reaches of the planets. Much of this material would have left the solar system entirely, travelling into other star systems, possibly into similar clouds around other young stars. But not all objects would have been lost to space. Some planetesimals settled when they reached interstellar space, not far enough away to completely escape the gravitational influence of the Sun, but far enough away that the predominant gravitational influence in the area is the tidal force from the Milky Way. Now, loosely guided by a gravitational limbo between the faint Sun and the rest of our galaxy, the objects in the Oort Cloud circle the Sun like bugs around a nightlight, suspended in galactic no man's land. It is also possible that the Oort Cloud could have captured planetesimal objects from other stars which were forming in the same solar nebula. Recent simulations of the early solar system have suggested that the Sun formed within an embedded open cluster of between 200 and 400 stars in much closer proximity to one another, before they each drifted away to the colossal interstellar distances that we see today. Most, if not all of these stars would have had protoplanetary disks and leftover debris which would have been either consumed by their planets or ejected. And as these stars receded away from one another, debris was scattered and traded between disks before falling into similar spherical shells like the one that surrounds us. As such, a large number of the Oort Cloud's objects are likely the product of gravitational interactions and exchanges between the Sun and its neighbours. Perhaps even the majority share of its contents are extrasolar in origin. We have known about the Oort Cloud for 70 years, yet it still remains unproven. The main line of evidence for its existence are long-period comets. Scientists agree that the Oort Cloud is the source of most of the very distant comets we see travelling into the solar system. Comets are chunks of rock and ice from the outer solar system, which are on a trajectory towards the Sun. Because they are frozen for much of their life, as they approach the Sun, their surface ice vaporizes, which creates a cometary coma behind the body, its most distinguishable feature. If it survives the vaporization and its encounter with the Sun, then it will pass by and leave the solar system again, where it will refreeze until it comes back around. After a few tens or perhaps hundreds of trips, depending on the trajectory, comets will eventually break down and disintegrate, never to be seen again. There are a few different classes of comet that enter the solar system. The first are ecliptic comets, otherwise known as short period comets, which orbit within about 10 astronomical units of the Sun and thus along the Sun's ecliptic plane. Most of these originate from either the Kuiper Belt or the scattered disk, another disk of trans-Neptunian objects which are scattered by the gravity of Neptune. The other type are long period comets, which take longer than 200 years to orbit the Sun and thus enter the solar system very infrequently. Most known long period comets have only ever been seen once, and the vast majority will go undetected. Some have orbital periods so long that the last time they entered the solar system, mankind didn't exist. The first people to consider the source of these comets were astronomers Ernst Öpik and Jan Oort. In the early 1930s, Öpik speculated that the most distant comets originated from a cloud orbiting in the outer solar system. In 1950, Jan Oort revised this idea to explain the abundance of comets we observe in the solar system today. Because most comets are primordial planetesimals which have been around for 4.5 billion years, you would expect that most of them would have either vaporized or crashed by now. And yet, we see an abundance of comets entering and leaving the solar system even to this day. Oort predicted that there must be a so-called comet reservoir in the outer solar system, a source of material which has managed to outlast the ages and remain populated with comets, similar to what Öpik had predicted. Oort also noted a peak in the number of comets whose trajectory would take them to around 20,000 astronomical units away from the Sun, suggesting that the source of the comet reservoir might be around this distance. He also noted that long period comets entering the solar system seem to come from all directions, not aligned with the ecliptic plane. He concluded that the reservoir must be a spherical structure and not a band or disk like the Kuiper Belt. He predicted an icy shell of cometary nuclei with a relatively isotropic distribution, like a cloud rather than a belt, and thus it received its name. Jan Oort had laid the foundations for uncovering the nature of the Oort Cloud, and in the decades since we have begun to understand its structure better. We now know that the cloud can be divided into two sections. One, the large spherical outer shell that we have discussed, and another smaller torus-like structure within. This torus, also known as the Hale cloud, is a vast circumstellar disk, marking the beginning of the inner Oort cloud at about 2,000 astronomical units, extending to at least 10,000 astronomical units, and possibly twice or even 3 times as far. Unlike the spherical outer Oort cloud, the Hale cloud is more analogous to the Kuiper Belt, albeit thousands of times larger. We know that the Hale cloud exists because it is the key to the mystery of the Oort cloud's apparent self-rejuvenating properties as a reservoir for long-period comets. The Hale cloud is estimated to have the highest concentration of comets found anywhere in the solar system, containing at least 5 times as many comets as the outer Oort cloud and possibly more, and these are regularly ejected by gravitational disturbances, sending them on trajectories to the outer Oort cloud. Over time, this process provides new objects to replace those which are being lost from the outer cloud as long-period comets. Furthermore, it is likely that the Hale cloud is also populated with comets from another source, the scattered disk. Around half of its scattered objects end up on outward trajectories, which eventually reach the Hale cloud and thus indirectly feed the Oort cloud. We've never managed to identify an object in the outer Oort cloud, but it is possible that the minor planet Sedna, which was discovered in 2003, may be a Hale cloud object. Sedna is classed as a planetoid, made of mostly water, methane and nitrogen. It is about 3/4 the size of Pluto, and orbits the Sun significantly further away. It takes Sedna approximately 11,500 years to orbit along its radically elongated and elliptical path, which takes it as near to the Sun as 76 astronomical units and as far away as nearly 1,000. At the time of this video, it is about 85 astronomical units away, and currently on a path back out into interstellar space. The Minor Planet Center, which is the official organisation tasked with gathering data for minor planets, classes Sedna as an object of the scattered disk. However, this has been disputed. Its wide-angled orbit takes it much further away than the orbits of scattered disk objects such as Eris, which only recedes as far away as about 97 astronomical units from the Sun. Sedna's trajectory will take it considerably further, and thus some speculate that it is an object of the Hale cloud. However, this has not been proven, and there could be any number of other natural explanations for this peculiar planetoid's bizarre orbit. The outer Oort cloud is much more diffuse than the Hale cloud. Estimates range in the number of objects contained within, but a good guess puts it at about 2 trillion. As many as 1 trillion of these objects may be larger than a kilometre, but each is scattered tens of millions of kilometres apart. The total mass of the outer Oort cloud is not known, but by using Halley's Comet as a generic example, the combined mass of the exterior shell would equal about 5 times the mass of the Earth, maybe slightly less. That is a comparatively small amount of material spread across an incomprehensibly vast expanse. As such, it remains difficult to spot the small, faint objects within. It is only when a gravitational influence, such as a passing star or the tidal force from the Milky Way, disturbs one of these objects and sends it on a trajectory towards the Sun where it becomes visible to us as a comet. We've managed to record a few examples of these over the years. One of the most recent was Comet Siding Spring, an Oort cloud comet which was discovered in 2013, before making a close approach by Mars in the following year. As it vaporized near the Sun, astronomers detected elements such as iron, nickel, potassium, zinc, chromium, and magnesium. At the time of its discovery, it was about 7 astronomical units from the Sun, but its orbital period is so long that it will take another 740,000 years at least before it re-enters the solar system again. Another example is Comet Hale Bopp, which was discovered in the summer of 1995. It was the most widely observed comet of the 20th century, visible to the naked eye for some 18 months, and was the brightest comet observed in decades, and the most prolonged period of visibility ever recorded. Comet Hale Bopp was found to contain argon and was also 25 times more depleted of krypton than the solar system average. These two discoveries are indicative that Hale Bopp has been colder than around -238 degrees Celsius for the majority of its life. Thus, it is thought to have formed in the Kuiper Belt before migrating outwards to the Oort cloud, where it re-entered the solar system as a long-period comet millions of years later. Finally, we have Comet Lovejoy, discovered in 2011 by amateur astronomer Terry Lovejoy. This comet is classed as a Kreutz sungrazer, a special type of comet whose orbit takes it very close to the Sun. In 2011, Comet Lovejoy did just that, approaching the Sun and passing through its corona. It emerged intact on the 16th of December, but was greatly impacted by the intense radiation and heat of the Sun. It then became visible from Earth during the Christmas holiday period, earning its nickname of the Christmas Comet of 2011. While we've never managed to identify an object within the Oort cloud, no less than 5 man-made spacecraft will eventually visit it, but these won't be 5 dedicated missions. They will be the remains of interstellar probes from previous missions, Voyager 1 and Voyager 2, Pioneer 10 and Pioneer 11, and finally New Horizons. At the time of this video, Voyager 1 is the furthest and fastest, but the inner edge of the Oort cloud is so far away that it will take well over 500 years for these probes to reach the Hale cloud, and between 12,000 and 25,000 years to cross out the other side. By this point, all 5 spacecraft will have been dead for some time. In the 1980s, there was a concept mission called the 1000 Astronomical Units, or TAU spacecraft, designed as a long-distance mission which could cover 1000 astronomical units in 50 years. Of its many proposed uses, collecting data about the Hale cloud and Oort cloud was one of them. But sadly, and despite renewed interest in the 1990s, this project never got off the ground. For the time being, the Oort cloud is just too far away to reach with a probe and transmit data back within any practical time frame. However, it might be possible to use improved existing technology to search for Oort cloud objects right here on Earth. In 2014, another concept mission was proposed to NASA's Discovery program, the Whipple mission. This mission proposed a dedicated observatory for detecting Oort cloud objects at a distance of 10,000 astronomical units, by using transit technology to detect objects as they pass in front of other stars and block out some of their light. Unfortunately, of the missions shortlisted by NASA for consideration, Whipple wasn't among them, but it was awarded funding to continue its research. Transit technology is a rapidly improving area of science, and so perhaps those advanced telescopes capable of detecting extrasolar planets around stars in the Milky Way might also be capable of detecting planetesimal objects in the Oort cloud as they pass in front of those same stars. Speaking of other stars, if the Sun formed as part of an open cluster of stars which were trading material, then shouldn't other star systems have their own Oort cloud-like shells? Well, in short, yes. It's a safe bet that a good number of stars in the Milky Way, including most of our stellar neighbours from the solar nebula, will have extrasolar Oort clouds just like our own suspended in interstellar space. But at interstellar distances, they are impossible to observe. However, if we find evidence of comets within these same star systems, then the chances are that there is some sort of Oort cloud-like source, and so it's fairly likely that many of the galaxy's stars house their own remote collections of comets. However, these probably won't be top of the priority list when it comes to investigating extrasolar stars in depth. Space is unbelievably vast. No matter what technology we develop or how powerful telescopes become, it doesn't change our size. Earth and every single thing that has ever happened on this unendingly complex planet has happened inside the space of a dot barely visible from its nearest neighbour. Star systems are so vast and far away for humans that we will probably never be able to understand another star system better than we understand our own. The Oort cloud is one of many fascinating things that we don't see when we look up at the night sky and at other stars. Each tiny speck of light from the sky abstracts the intricacy of its system, from its planets and moons right out to its Oort cloud, the vast hidden shell that lies in the space between stars.